You don't usually think about hydrogen when you think about heat. You think about electricity, wind turbines spinning, solar panels stretching across deserts, electrolyzers quietly splitting water somewhere behind a fence. That's the version of hydrogen most people understand. Clean, simple, increasingly familiar. But there's another version, one that doesn't use electricity at all. One that runs on heat so intense it begins to rewrite the rules of chemistry itself. And if you follow that path far enough, you end up somewhere most people never look. Inside a system that works perfectly on paper and almost nowhere in reality. This is thermochemical hydrogen, and it might already be good enough to replace electrolysis, so why hasn't it? Because this isn't a story about chemistry. It's a story about everything around it. It starts with a simple idea. What if you didn't need electricity to make hydrogen at all? Water is just hydrogen and oxygen bonded together. Break that bond and you get fuel. Electrolysis uses electricity to do it. But thermochemical cycles take a completely different path. They use heat. Not warm heat, not comfortable heat. Industrial heat. Relentless heat. The kind that pushes materials to their limits and forces molecules to behave differently. Instead of pushing electrons through wires, these systems push chemistry itself through a loop. Water goes in, heat is applied, reactions unfold. Molecules split, recombine, and cycle back. Hydrogen emerges, oxygen is released, and the original chemicals regenerate, ready to do it again. Nothing is consumed except water. It feels like something that should already be everywhere. And in controlled environments, it works exactly as designed. One of the most advanced versions is the sulfur iodine cycle. It operates at temperatures most industrial systems try to avoid, 800 to 900 degrees Celsius. At those temperatures, sulfuric acid begins to decompose. Iodine reacts. Hydrogen iodide splits apart. Each reaction feeds the next, forming a closed loop that continuously regenerates itself. If you diagram it, it looks almost flawless. No wasted inputs, no emissions beyond oxygen, no dependence on electricity. Just heat, driving chemistry in a perfect loop. But then reality starts to interfere, because at 900 degrees, nothing behaves the way it does on paper. Metals soften, corrosion accelerates, seals fail, and the very chemicals that make the process possible begin to attack the system holding them together. So engineers stepped back and redesigned the system. They created a second version, the copper-chlorine cycle. Same idea, same goal, but at much lower temperatures, around 500 degrees Celsius. Suddenly things look more practical. Materials last longer, components become easier to manage. The system can now connect to more realistic heat sources, advanced nuclear reactors, industrial waste heat, even hybrid configurations that use a small amount of electricity to stabilize the process. On paper, it's a breakthrough. Lower temperature, lower stress, better economics. But something still doesn't work. Because even when the chemistry improves, the system still doesn't scale. And this is where everything changes. Because the real problem was never inside the reactor, it was always outside of it. Thermochemical hydrogen doesn't just need heat. It needs the right heat. Not intermittent, not seasonal, not dependent on wind patterns or market prices. It needs constant, high-grade, precisely controlled heat, delivered every hour, every day without interruption. And that kind of heat doesn't exist everywhere. In fact, it almost never exists where hydrogen is actually needed. So now the system starts to fracture. The chemistry wants one location, the market demands another. And connecting the two isn't simple. You're no longer building a hydrogen plant. You're building an entire energy ecosystem. Heat source, chemical reactors, separation units, storage systems, infrastructure, all synchronized, all interdependent, all vulnerable. And if one piece fails, everything stops. This is the part no one talks about. Because hydrogen isn't just about efficiency, it's about utilization. It doesn't matter how efficient your system is if it only runs half the time. It doesn't matter how elegant your chemistry is if maintenance shuts you down every few weeks. It doesn't matter how low your theoretical cost is if your system spends most of its life offline. Thermochemical hydrogen pushes systems into extreme conditions. High temperatures, aggressive chemicals, multi-step reaction loops that depend on precision. If one reaction drifts, the loop destabilizes. If one material degrades, the system shuts down. A system designed to run at 800 degrees shutting down for even a few hours isn't just inefficiency, it's economic collapse. Every shutdown reduces utilization. Every reduction increases cost. And suddenly a system that looked superior in theory becomes uncompetitive in reality. This is the hidden tension. Thermochemical hydrogen promises simplicity, Water in, hydrogen out. But it delivers something very different. Complexity, reactors, loops, separations. Material science challenges, heat integration, operational risk. And that complexity doesn't just affect engineering. It affects money. Because investors don't fund chemistry, they fund reliability. They fund systems that run predictably for decades. Systems where risks are understood, where downtime is rare, where performance doesn't collapse under pressure. And today, thermochemical hydrogen struggles to meet that standard. Not because it's broken, but because the system around it isn't ready. And that creates a strange reality. You have a technology that could outperform electrolysis. That could potentially deliver cheaper hydrogen. That could decouple hydrogen production from electricity entirely. But it can't survive in the system we've built. So it waits. It waits for nuclear systems to scale. It waits for industrial hubs to align heat and hydrogen demand. It waits for materials to catch up. It waits for financing models to understand it. And while it waits, electrolysis keeps winning. Not because it's better, but because it fits the world we already have. Electricity is everywhere, this kind of heat is not. And that single difference changes everything. And here's the uncomfortable part. If nuclear scales faster than expected, thermochemical hydrogen doesn't compete with electrolysis. It replaces it. But if you zoom out far enough, this stops looking like a failure and starts looking like a preview. Because thermochemical hydrogen isn't a standalone technology. It's a system technology. And system technologies only win when the system is ready. In a world where nuclear reactors sit next to industrial plants, where hydrogen demand is constant and localized, where energy systems are fully integrated, this doesn't just work, it dominates. So the question was never whether copper, chlorine, or sulfur iodine cycles work. They do. The question is whether the world they need will arrive in time. Because energy transitions don't wait. They move with the infrastructure that exists, not the one that should exist. Right now, that infrastructure favors electricity. But systems evolve, and when they do, the balance shifts. Quietly, gradually, then all at once. And when that moment comes, the technologies that looked too complex, too fragile, too dependent, might suddenly become the only ones that fit. That's the paradox of thermochemical hydrogen. It's not early, it's waiting for the rest of the energy system to grow up.